Now, after we discuss the concepts and the formulas for sample variance and sample standard deviation, let's practice how to calculate them. We know the sample variance and the sample standard deviation are important measures of dispersion, that is, in a data set, in a variable, what is the typical discrepancies between individual values and the mean. And we want to see this inequality and the discrepancy between individual values and the mean for the data set as a whole. Here we use this data set. In this data set, we have 7 cases, and each case has their own value. We first calculate the mean, and the sum of 7 cases is 45. 45 divided by 7 gives us 6.4. That's the sample mean. Then we calculate the deviation for each individual case. 5 minus 6.4 is negative 1.4. 8 minus 6.4, we have deviation 1.6. You do the same for every single observation. This is the deviation. And if you find the sum of all deviations, it turns out to be 0, because there are positive deviations, there are negative deviations. If you find the sum of all individual deviations, it turns out to be 0, and that's exactly we do not use deviations. We use squared deviations and try to use squared deviations to calculate the measures that give us a sense of dispersion in the data set. So after we find deviations, we square all of them. Negative 1.4 squared is 1.96. Is positive. All the negative values, when you square them, they will become positive. 1.6 squared, 2.56. You do the same for all individual deviations. You find the squared deviations for all cases. Then you find the sum. Okay. This is the formula for sample variance. This sum goes to here. So you can really see how do we apply the values in the formula. At the bottom is number of cases minus 1. So we obtain sample variance 3.29. You find the square root of 3.29. You obtain sample standard deviation. So sample standard deviation is 1.81. And 1.81 tells us the typical difference between the individual values and the mean is 1.81 for this data set. In comparison, if you have a different data set, the typical spread, the typical difference between the individual value and the mean is 3. You know that for the second data set, that the spread is a lot bigger than this data set. There's more inequality among cases. So that's the practice of how do we apply, how do we use these formulas. Now, in the context of measures of dispersion, there is this measure of coefficient of variation, which is the ratio between the sample standard deviation and sample mean. And sometimes you also can express that ratio in terms of a percentage. And in that case, we just use this ratio multiplied by 100. Why do we calculate the coefficient of variation? Now let's look at this example. There are 2 places, 5 workers in 2 places. They have their own individual income, maybe hourly income. And when you come to calculate the deviation, the standard deviations for both places, they're about the same. The first place have a standard deviation 3.1. The second place have a standard deviation 3.0. So it looks like both places they have the same amount of income inequality among individual workers. We know that the standard deviation measures the typical spread among between individual cases and the mean. And both places have this spread 3.1 or 3.0 about the same. But if you use the standard deviation divided by the average income of two places, you can really see the relative difference in income between individuals, and the mean is very different between the two places. First place, 3.1 divided by 15.2, you have about 0.2, 20%. The 20%, the income inequality relative to average income is about 20%. Is about 20%. For the second place, 3 divided by 5.6 is 54%. Income inequality in relation to average income for the second place is 54%. So relative income inequality in the second place is a lot larger than the first place, even though they have about the same amount of the absolute amount of income inequality. So this does really give us a measure of the relative differences in terms of income to the average income. So that the coefficient of variations is significant in a sense that it describes the standard deviation in relation to the average income. Two places may have the same amount of standard deviation, but they may have a very different level of average value. And the same amount of standard deviation may appear to be very small for one place, but appear to be very large in another place. So that is the usefulness of a coefficient of variation. Now, let's use the same data set to calculate the coefficient of variation. We already calculated a sample variance and a sample standard deviation. 1.81 is a sample standard deviation. That number is divided by sample mean 6.4. You obtain 0.283. You times 100 give you 28.3%. So that's how we calculate the coefficient of variation. Measures of a distribution shape. Shapes of a distribution. A variable may have a symmetrical distribution. All data values are well balanced, evenly spread among both sides of the center. When that happened, we know the mean equal to the median. Okay. Symmetrical distribution. You may also have a shape we call uniform distribution, in which each data value occurred with the same frequency, kind of a flat, uniform distribution. You may also have bimodal distribution, which means that there are two distinct peaks. Here, look at these examples here. Symmetrical distribution, uniform distribution, all the values occurred with the same frequency. This is obviously bimodal distribution. And a distribution may also be asymmetrical. And obviously, all these shapes indicate asymmetrical distribution. And probably one side have more case on the other. One side have more higher frequency, and so on and so forth. And that's several cases of asymmetrical distribution. We're particularly interested in this kind of shape and this kind of shape. Okay, that brings us to the next slide. This kind of shape with a longer tail extend to the right, to the higher value direction. This kind of shape is called positively skewed. Okay, you have many smaller value closer to the lower value end, but a few large cases extend to the right. This shape of distribution is an indication that in a data set there are few large outliers, and they try to push the average to the higher value direction. When we have a positively skewed data set, the mean is larger than median. Why is that? Look at this one example. This is obviously symmetrical distribution. You have either equal number of cases on both sides of the center. At the center, the mean equal to the median. Now, if you just move one case to the right, to the direction of a large value, first, what would happen to the mean? The mean will become larger because we already discussed that if you introduce extremely large value, that would tend to pull the mean to be higher. So the mean for this data set is larger than the mean for this data set. But the median between the two data sets are the same. This is a median of this data set. This is also the median for this data set. On both sides of the median, you have equal number of cases. So the medians are the same for both data sets, but the mean for the second data set is larger. So from there, we can conclude that for this case, when you have a positively skewed data set, the mean is larger than the median. So this shape indicates that there are large outliers in the data set. In contrast, when you have a data set that has this shape, you have a few extremely small value drag this tail toward the smaller data set direction. That is an indication that you have a few very small outliers, and longer tail extend toward the left, toward the lower value direction. When that happens, the mean is smaller than the median. Now we actually have measures, have index number to describe skewness. This is a formula we call skewness. On the top is a sum of cubic deviation cubed over all cases. Then you find the sum. At the bottom is n multiplied by sample standard deviation raised to the third. When this measure is larger than 0, when it's a positive number, this data set is positively skewed. When this number is negative, the data set is negatively skewed. When this index number is close to 0, we have a symmetrical distribution. Okay, now this is how do we actually calculate this value. Now we have the same data set. Here the deviation, squared deviation cubed. How do you calculate the cubed deviation? You can simply use deviation multiplied by the squared deviation. That gives you this value. So it has negative sign. The negative sign carries over here. After that, you find the sum over all cases to find a big sum right here. The sum of cubed deviation. This is the formula here. This big sum goes to here. At the bottom, number of cases 7. multiplied by the standard deviation raised to the third. So 1.81 raised to the third is 5.93. You complete the calculation, you obtain the skewness 0.36. A positive number. That means the data is positively skewed. Then you have the measure of kurtosis. The measure, this index number measures the peakness or flatness. So-called peaked or flat distribution is in comparison with benchmark normal distribution. We use a normal distribution as a benchmark. Is more peaked than normal, we call it peaked distribution. Is flatter than normal, we call it a flat distribution. So the benchmark is normal distribution. We're going to discuss normal distribution later. This is one formula for kurtosis. On the top is a big sum of the deviation raised to the fourth power. At the bottom is number of cases multiplied by the standard deviation raised to the fourth power. The textbook use this formula. So if this index number is larger than 3, is peaked. Is smaller than 3, is flat. And if it is equal to 3, it's not peaked, not flat, just normal. Okay. An alternative formula is this. It's called excess kurtosis formula. This formula is almost the same as the previous formula, except that same thing here, same formula minus 3. So that would make, if this index number larger than 0 is peaked, negative smaller than 0 is flat. If it's close to equal to 0 is normal distribution. The software program SPSS, which you're going to use this formula. So in our in-class activity, we can use this formula. We use this formula. Okay. Now let's practice to calculate kurtosis here. Okay. This same formula, same data set, deviation here raised to the fourth power. Okay, for every single observation. Then you find the sum right here. This sum right here. This is the formula. On the top is where the sum go. At the bottom is where the number of cases multiplied by the standard deviation raised to the fourth power, and 1.81 raised to the fourth power is 10.733. The whole thing minus 3 give us negative 2.01. So kurtosis is negative, so the distribution is flat. It's flat. Okay. I hope this helps. I see you next time. Goodbye.